Okay, so this is the second part of section 1.15, bottom of page 128 and top of page 129. And so you have 100 people that have a virus. They infect 2 more people each, and then so forth and so on and so forth. And so here they're kind of pretending that, like, say this is just one person. So this one person is going to infect 2 people, and so like this one person here is going to infect 2 people, but in reality, these are 100 people that are each going to infect, 200 people basically. And then pretend this is one person, they infect 2, then each of these are going to infect 2. But in fact, this is not really standing for one person. This is 100 people, so they're infecting 200, and then this other person is also impacting 200. Okay, and again, if you think of these as one person, they impact 2, 1, infect 2, 1, 2, and 1, 2. But in reality, this is 100 people right here. And so this is 200 people, another, 200. So now we're up to 400, and then so forth. All right. So obviously this infection is going to spread very quickly, right? And so again, what am I doing each time? I'm doubling. And so if I'm multiplying by 2 all the time, this is geometric. But again, real life starts at 0. So the nice thing about these is you don't have the fix. You don't have the n-1 thing. So starting amount, day 0, how many people are infected? 100. What math are you doing? You are multiplying over and over by what? 2. And again, think about it. Repeat multiplication is exponential. It's exponents. So, for example, on day 6, how many times did I multiply by 2? Multiply by 2 once, twice, 3, 4, 5, 6. And notice that equals that. So if we're on the nth day, then that's your exponential. That's your nth day. And again, the math works for 6, because for 6, you would have a starting amount of 100. And then you'd multiply by 2 over and over and over 6 times. And if you type that in your calculator, you should get that number. That's kind of how you can kind of see if your formula is right. Now, as far as graphing this, at 0, I would be, and again, my numbers are pretty tiny here. 0, I'm just barely here, and so forth, because this is 20,000 and so forth. But notice that it starts out really slow. So at first, it almost looks like, it's linear. But then as time goes on, it just gets exponential. Notice it doesn't make a line. This is exponential growth. All right, I'm going to pause it for a second, and then we'll scooch down here and look at some of the other pages. Okay, so you can kind of go over and read this next page if you would like. But down here at the bottom, they talk about the vocab words for exponential growth and exponential decay. And if we flip to the next page here. So exponential growth is the top one here on the left, gets bigger and bigger and bigger, kind of slow at first, but then it takes off. Exponential decay starts big and like half, and it gets tinier and tinier and tinier over time. These are not linear, so they're not arithmetic. They are definitely geometric. So go ahead and try number 4, and then we will come back and talk about it. Okay, so a company wants to project growth using both linear and exponential change to see the long-term effect. Company begins with 150 clients. The CEO wants to project growth using 5 new clients per month versus a 10% growth rate. Okay, so we can make a chart for both of these. We could have kind of our input and our output. So we could look at the first one here. So at 0, when you start doing the data, you have how many people? You have 150. And then every month, so 1 month, 2 months, 3 months, 4 months, 5 months, 6 months, 7 months, you're going to gain what? 15 new clients. So 165, 180, and I could keep filling out my chart. Okay. So then our goal is to write a formula to predict this. All right. And so again, if we keep adding all the time, it's arithmetic. So our formula would be something like our starting amount, which again, in real life, remember, it starts at 0, but this is the amount that we have at 0. So at time 0, we have 150 people, plus what are we adding over and over and over again? We're adding 15. And then repeat addition is multiplication, so it would just be n. And again, if you want to check your answer, after 3 times, how many times did we add 15? We added 15 once, we added 15 twice, we added 15 3 times. So when n is 3, I'd sub in 3. That would be, 45, which is 195, which it checks out. So I know my formula is right, okay? And then the second thing is they want to know how many months it will take to get to 500 clients. Now, kind of depends on if we know algebra or not. If we don't, then what we're going to do is sub in numbers like 3, 4, 5, 6, 7 into our formula until we get to 500, okay? So you might want to jump and try like 10 and try 20. Like if I try 20, if I sub in 20 into my formula, and again, you can use a calculator, 20 sets of 15 would add, 300 to the mix? So 150. So I'm at 450. So I know 20 is close. So then I might want to try 21, 22, 23. If you remember your algebra, I'll come over here, you can write an equation. So I want to know when this is going to equal 500 people. I can subtract 150 from both sides, because remember you want to isolate your variable, and you get 15n equals 350. Then divide both sides by 15, and you get n is about, I don't know, what is it, 23.3 months, so about 23 and a third months or repeating or whatever. So that's if it's linear. All right, so let's look at the second thing is they want to look at if it's exponential. So we've looked at kind of the linear part. Let's do exponential next. So I'm going to pause this, try to make a chart for the exponential, try to write a formula, and then we'll talk about this. Okay, so now we're looking at the exponential model. So again, at time 0, when they started doing the data, they had 150 people. But now we're doing exponential, and so instead of 15, they're growing by, let's see, versus 10% growth rate. All right, so remember, if something's growing by 10%, the multiplier is 110% because you're keeping the previous value, you're growing by 10%. So your multiplier is 110. So what I'm going to do here is to fill out my chart is I'm not going to clear my calculator. I'm going to type in 150, and then I'm going to multiply it by 1.10. So I'm going to take 150 times 1.10, and I get 165. But see, now it's going to grow from there. So now I'm just going to type in another, don't clear your calculator, just leave what you have in, and then hit enter, and I get, 181.5. So that's the answer to this. Well, then I'm going to increase it again. So don't clear your calculator, multiply by 1.10. You get the new amount, 199.65. Then again, we just keep multiplying by 1.10. So we're just using that multiplier to predict future values. And again, with people, you can't have part of people, so we'd have to round at a certain point. All right, so what's our formula? Well, again, real life starts at 0. So how many people did I have at time 0? I had 150 people. It's growing by 10%, so it's 110% is my multiplier. Notice if they were losing clients, we'd take 100% minus the 10%, and they would only be keeping 90% of their clients, so we'd use 0.9 here if it was exponential decay. But this one's definitely growing. And then again, it's exponential. We're repeat multiplying, so our variable is up high. All right. Now, this one's a little harder to figure out when it's going to hit 500 clients. You need logarithms, actually, which you probably don't know. So what you're going to want to do is just guess at n. So you might want to try typing in like, say, I don't know, these are getting big pretty fast. So maybe try 10. And then see what your calculator gives you. If that's too small, then maybe try 11. If that's too small, try 12. But your goal is to get 500. And for that one, it is going to be about 13 months. So if you try 13, it should be close to 500. All right, try number 5, and we'll pick up there. All right, so let's look at this one. City planners are trying to write formulas to predict the future values. And then they also want to know when, let's see, they only have resources for what? 200,000. So, but they do know they only have, for each scenario, write a function, and when will it be at its max capacity? All right. So let's do the increase. If it's 5,000 per year, is that exponential or linear? So basically, linear is arithmetic when you add all the time. Geometric is when you multiply all the time. So if I'm just increasing by 5,000, I'm just adding all the time. So again, at time 0, what is my starting amount? How many people did I have? So it looks like they're starting out at 100,000 people. So 100,000 people, adding constantly more and more people, 5,000 per year? So that's your n. We'll come back to this in a second. Which else is linear? This one, I'm going up by 8,500 all the time. So 100,000 is your starting amount at year 0. And then instead of adding 5,000, I'm adding 8,500 people all the time over and over and over again. Again, these are going to be linear. They're going to just be lines growing up. But this is growing by a percent, which means it's going to be exponential. So my starting amount is 100,000. My multiplier is what? Well, I have 100% of the people I'm keeping, right? Kind of like Ankeny, it keeps growing. I'm adding 2.5%, so that's 102.5%. So my multiplier is 1.025 in decimal form. And it's exponential, so your n are variables up in the exponent, because you're repeat multiplying all the time. And then this one, same thing. You start out with 100,000 people. You're increasing, so you're keeping everybody and adding 3% more, so 1.03 in decimal form. And you're repeat multiplying all the time, so that's exponential. Now again, if you want to figure out when these things equal 200,000, kind of depends on how much algebra you remember at this point from high school. So here you could equal 200,000. You could subtract the 100,000 from both sides. And that gives you what? 100,000 equals what? 5,000 n, and divide. And so you should end up with about, or exactly 20 years. So after 20 years, they're going to kind of be at capacity. This one you'd solve the same way. Bring 200,000 over, subtract your 100,000, but then divide by 8,500 instead. These two are, you would still set equal to 200,000, so we'll do this bottom one. So top one would be the same. You'd equal 200,000. But again, exponential, you can't just divide and stuff because the variable's up here. So what you're going to have to do is just keep guessing until you get 200,000 people. So again, you might want to test 10 years and be like, oh, wait, too low. Try 20 years. And then you're like, oh, try 30 years. Nope, too high. Maybe 25 years, too high. And then try 24. So you just keep shoving that in your calculator. So if you take 100,000 times 1.03 and raise it to the exponent of 24. Some of you, that exponent key is going to look like this, like a little caret guy. Some of you, it might be x to the y. Kind of depends on. But anyway, if you do this, you're going to equal pretty close to 200,000. So here you just keep guessing over and over and over again until you get it. And I think that one ends up being an answer of 29 years. This one, you don't have to guess. You can subtract and divide. And that one, I think, ends up being 12 years. All right, let's see. Do we have anything else for this section? I don't think so. Let me go back and pick up that one that I had to cut off the video the other day. So let's jump back there and do that quick if we have a few minutes. Go back to page 106. And I'm going to pause this and we're going to finish that problem about the tuition increase that I ran out of time for. Okay, so the other day, this rest of this video got cut off on page 106. And it's talking about percent increase on tuition. So if these are the rates, you can't add those up because the percent works on, say tuition's $100, which is an easy number to make up because you can subtract it easy. So it's 108% increase. That answer, don't clear your calculator, multiply by 5%, which is 105% increase. Don't clear your calculator. Now the next year it's 109% increase because you keep and add. Keep doing that with all of these and you'll notice you'll get this amount. And the reason I picked 100 is strategic because percent increase is the change divided by the start or the original. So the change here is 49.45 about over the original, which is 100. So if you divide that and multiply by 100, you can see that that's going to stay the percent. So that is a 49.45%, right? And so the reason you can't add the percents is because you keep changing what you're doing the percent of. You keep getting new answers over and over and over again. So you can't add the percents. Sometimes you can add percents or an extra credit, like if you get a 98% and the teacher gives 100% extra